All right, silly people, here's the situation. We're looking for a generating function which produces this canonical transformation, that those Q's and P's up there. Um, I think the point of the problem is that you can't really do that. You can't have a generating function that works for all values of alpha. I, and it kind of uh, suggests this by asking if it works for the extreme cases. I'm going to show that this generating function, which is of the form f1, um, works for general um, angle alpha, but not for all of them. Um, so I came up with this generating function off camera uh, because it's kind of a weird process to get there, but I swear it works, and I'm sure you can find other generating functions that work. So we're gonna prove that. Um, First, let's take the partial derivative with respect to big Q um, to show that it's just minus the big P equation from above. So that's going to make us have negative little q tangent alpha divided by sine alpha tangent alpha plus cos alpha minus p cos alpha. P cos alpha. So it doesn't quite look like minus big P yet, but just give it a second. We're going to expand the tangent functions. So we're going to have q sine alpha up top, and then we're going to take the cosine to the bottom there. Oh my goodness. Cosine alpha. We have sine alpha there, sine alpha up top, cosine alpha on bottom, plus cosine alpha all over that stuff. Minus p cosine alpha. You can probably already see what we're going to do, but we're going to distribute that cosine alpha so that we just have sine squared alpha plus cosine squared alpha on the bottom, which you know is just 1. So minus q sine alpha minus p cos alpha, which is exactly minus big P. So that relation works. Now we should prove that del f1 del q is actually equal to little p. To do this, let's first put little p in terms of um, big Q and big P, and possibly even little q, just by rearranging the canonical transformations given. So first, using the first equation, I'm literally just going to solve the first equation for q. Q is equal to big Q plus little p sine alpha over cosine alpha. And then plug this into the second equation to get big P is equal to, it's going to be Q tangent alpha plus little p sine alpha tangent alpha. Yeah. Plus p cosine alpha, and then solve for little p, which is going to be big P minus q tangent alpha divided by sine alpha tangent alpha plus cosine alpha. That looks familiar. So let's just do that then. Looking back at our generating function, that guy there, taking the partial derivative with respect to q, we'll just have us getting exactly this. So the generating function works for general alpha. Any alpha that's not 0 or pi halves, this will generally work. I'm going to show you why both of these are kind of a problem at the extreme examples. So for alpha equals 0, what does this mean? Well, if you just look back at the canonical transformations, that just means q is equal to, or big Q is just equal to q minus nothing. Big Q is equal to little q, and big P is equal to little p. So it's the identity transformation. Nothing changes in the system. If we plug that into our generating function, which I'm going to actually grab and copy and put it down here for science. If you plug that into the generating function, then okay, tangent of 0 is 0. So none of that. Yeah. Tangent of 0 is 0 again. And then we have a 1 on the bottom minus q cosine of 0 is 1. So it's just that. So it's big P little q minus big Q little p is this form of the transformation function. And it still works even. So taking the partial with respect to del q is actually now big P, which is not what we wanted. And also taking the partial with respect to big Q, you get minus P, which is equal to minus big P. So literally the opposite of what we wanted from the generating function is what we now have, which just goes to show this generating function doesn't work at these extreme values at all. What about if we look at just alpha equals pi halves? Alpha equals pi over 2. Disgusting. Alpha equals pi over 2. Then the transformation equation reads q equals minus p, p equals q. This is directly switching places the generalized coordinates with canonical momenta in phase space. So it's pretty much taking the transpose of the situation in phase space, which is weird to think about, which is pretty cool. Does the generating function at this value actually work? Turns out, no. No, it doesn't. Because tangent at pi halves is equal to infinity. So if we do that, we have a minus infinity up top. with a infinity on the bottom plus that's going to be nothing, and then minus nothing. Cosine of pi halves is 0. So we have a minus infinity over a positive infinity, which means we can't really take partial derivatives of it. It's a meaningless, improper, undefined quantity that doesn't work at all. So we're calling this whole situation a bust. You can try it with other forms of the generating function f1, f2, all the way up to f4. None of them really work, and I've done them all myself. They just don't. Alas. And that's kind of the point of the problem.